All right, hi, all. Thank you for coming to this. I didn't realize I was still muted. I thought I'd unmuted there for a second. So thank you very much for coming to this, where we get a chance to talk to all of you guys about the observatory and give you a quick update on what's going on with the observatory, and also get a chance to hear about some fantastic science that's going on, typically with our telescope or with some of the other science going on in the community. As always with these webinars, please use either the chat or the Q&A to ask your questions. That keeps it very simple for us. We'll then repeat the question out before answering it. So feel free to use the Q&A or the chat at any time you like, and then we'll go through and look for those questions at the end of each section of this. So today we get a little bit of news from me. I'll just let you know what's going on at the observatory very briefly. And then we get to hear from Jill Malusky, who's going to talk to us a little bit about the fantastic milestone that was just passed for the Green Bank telescope. And then finally on to the main event, which will be Loren from West Virginia University, who will be talking to us about ionized gas in the galactic midplane. So with that, just a quick update on what's going on in the observatory. Of course, we still have COVID-19 around the state of West Virginia, and the percentage of positive cases has remained steady for quite a few weeks now, sitting around 2 to 4% of all the tests that are taken. Of course, we're under a mask requirement for everybody indoors, or where you can't socially distant. School sports have started, so the high school and middle school sports have all started up within the state of West Virginia, and school is starting within 2 weeks of the state. In spite of the school sports starting, certainly within our county, we haven't seen any increase in COVID-19 cases, and at the moment, Pocahontas County has no COVID-19 cases reported, which is fantastic. GBT remains in 24-hour, 7-day operation, and that's been going along great, and the science for the telescope continues to be fantastic. Our visitor programs remain canceled at this point, although we're working actively. Our education and public outreach group is working hard at coming up with a way to resume some limited tours, at least on site, some walking tours, and other ways to let people start to learn again about the site and stop in and interact with us. So hopefully over the next few weeks, we'll be getting to announce that fact. Other great news at the observatory: in spite of COVID-19, we continue to hire, which is wonderful. So next week on Monday, we have 3 new staff members joining us. We have Jesse Bublitz, who's joining as a postdoc into the scientific staff. Flora Pagnelli is joining us as a radar scientist to help us with our new radar program on the GBT. And we're welcoming back Jonah Bosserman as an electronics technician on Monday. We're very excited about all 3 of those hires. Continue to just grow the staff, even as we don't quite get to meet people face to face, but at least we know what everybody looks like with a mask on, and someday we'll get to see people without that. So other things going on at the observatory, just my last quick update slide is a reminder that the Argus 144 meeting is next month. The talk schedule is now online. If you go to our website and go under events, you'll be able to see that. We also have an observer training workshop coming up in October 13th to 14th. Currently, we are full. That observer training workshop is completely full. However, you can go in there and sign up if you want to make sure you get information for the next workshop, which is scheduled for February of 2021. That one will also be held remotely, just like the October one will be. And then we also have a planned single dish training school. This is the week-long school where we get into a lot more of the details about single dish radio astronomy. This is a school we're happy to be having Eric Stibo with us again at this school. It's currently scheduled for May of 2020, and the details for that school should be released very, very soon. So we'll be keep an eye out for that on our website. We'll be sending out announcements as well with our newsletter. So with that, I'm happy to say that this is now the scientific staff at Green Bank. So the numbers are ever growing, which is a fantastic place for all of us to be. And we're very happy to see the new faces onto the screen. So with that, I'm now going to hand this over to Jill Malusky to talk to us about the 20th birthday of the GBT. So off to you, Jill.
Okay, great. Hi, everybody. I'm just going to get myself set up to share my screen. And while I do that, if you like my Zoom background, go to our website. We have a bunch of digital swag you can download for your Zoom meetings, for your smartphone, all sorts of stuff. So let me get this ready to go here. Can everybody see that okay? Thumbs up? Hope so. Okay, well, I'm just going to go ahead and let this play in the background. This is an example of some really great archival footage we have from the construction of the GBT telescope. There are a lot of different ways to slice the anniversary, considering how long it took to design, engineer, construct. August 25th was the day of the dedication. So we're starting our 20th celebrations there. And we've begun to share lots of different resources online. These archival videos are available on YouTube. And the best way to get there is to go to our Green Bank Observatory website, to navigate to this top row of buttons that we see here. Here's all our great social media. So you can actually click right on the YouTube button right there and watch the GBT time lapse that we just saw. You can watch the full dedication ceremony, which I think that runs about an hour and a half or 2 hours. You can also watch a fantastic video, which I'll show a couple of screenshots from, that was never released. It's a 20-minute piece interviewing a lot of the great minds and great people behind the design and construction of the telescope. So, as I said, between August 25th and actually April of 2021, we're going to be celebrating our 20th anniversary. And the EPO department has a lot of great programs planned. They're going to be working with the science division to conduct some oral histories. So keep an eye out for that. We'll be putting out calls to interview people who were a part of behind the scenes of building the telescope and scientists who've used it over the years. And you'll get interviewed. It'll be recorded and archived and shared for staff to enjoy and the public to enjoy. On Facebook, on the 25th, we just launched the Green Bank Telescope Design Challenge. So we can see Sophie there, a member of our EPO team. She gives a great instructional video on how you can do this activity. Usually it's a program you can take when you come to the Science Center, whether it's a field trip or a scout group. Now anybody can do this at home. If you are having to teach the kids some great STEM activities, if you know a teacher who's looking for things for the classroom, an astronomy group, everybody can jump into this Green Bank Telescope Design Challenge, follow our rules, watch some instructional videos, and share what your telescope looks like. So we're looking forward to that. Again, there's lots of great resources you can access on our website through our social media. And some other examples of that, we'll be having some great tweet threads that some of the EPO staff are putting out, highlighting different folks and milestones, having lots of videos and photos on Instagram. These are some of the account names. Here's a great photo. I'm sorry, Jay, I couldn't help but share it from that never before released film about, again, the great minds, the great folks behind the construction of the Green Bank Telescope. So you can see this great interview with Jay Lockman on our YouTube channel. And also Martha Haynes. So I'm going to end my little share here with a great quote from Martha. This is something we shared on the 25th. So this is actually an excerpt from something that she says in that never before released film that you can watch. We can either be very safe and build something that's very predictable, that takes absolutely no risks, that we absolutely know how to build, or we can try to use our imaginations. It's a risk, but we should be willing to take risks. And what a fantastic risk it's been, because now we're here celebrating the 20th anniversary. So if you have any questions about any of the things I mentioned briefly, feel free to shoot me an email. All our contact information is available. We even archive and share these community Zoom videos on YouTube. So just reach out and let us know. Thank you.
All right. Thank you, Jill, for that. And again, as she said, please just put any questions you have in the chat or the Q&A, and we will answer them as we go. I will note too, thank you to the couple people that pointed this out, the single-day school is not, of course, in May of 2020. That has passed. The year is going far too quickly for me. It is in May of 2021. That is next year, which is why I'm announcing it. So look for that announcement. So with this, I'm very happy to introduce then Loren Anderson and hand the screen off to him. So Loren Anderson from West Virginia University. It's all yours, Loren.
Great, thank you. Share here. So I occasionally have internet issues and I drop out for 10 seconds. If that happens, I can still hear you. So just tell me I've done that and then we'll have a 10-second break and then I'll start talking again. I cannot figure out what's going on. It happens, but not necessarily every day. Anyway, so I'm Loren Anderson. I'm from West Virginia University, just 3 hours north of Green Bank. and I'm going to tell you all about ionized gas in the galactic midplane. And I added that word diffuse ionized gas because I changed the slides a little bit just before the talk. So this is work that I've been doing basically since I was a graduate student when I started using the GBT to look at ionized gas. So what I'm going to say is that we do not really understand midplane ionized gas. There are lots of H-alpha surveys which are fantastic and really very sensitive, more sensitive than what we can obtain in the radio, but they're distance limited due to extinction. And so in the radio, we have better tracers that go deeper. And although they're a little bit less sensitive, as you'll see in the coming slides, we have worked hard to play with the configuration to get more sensitivity out of it. Another tool you can use are pointed observations, which measure diffuse gas emission at select locations. But until pretty recently, the sensitivity was limited, and the resolution was oftentimes not great. The resolution turns out to be really important because the galactic plane is littered with H2 regions. And if you want to separate the emission from H2 regions, so individual massive star formation regions, from the more diffuse ionized gas that we know pervades the disk, you really need to have very good spatial resolution. Otherwise, your beam is going to collect emission from both at the same time. There was a survey that was begun in the early 2000s and not yet published until 2013, and then followed up in 2019. And that provides large-scale spectroscopic maps of ionized gas in the plane. That's known as SIGMA, done with Arecibo, and it maps radio recombination line emission, which is what I'm going to be talking about for the rest of this talk. It's limited in the declination to about 32 degrees galactic longitude. That is just the declination limit along the plane as seen by Arecibo. And then it goes up to about 70, which is the other limit imposed by the design of the Arecibo telescope. And so it kind of misses a lot of star formation that we would be interested in that is located more towards the galactic center. It's beam sampled at about 6 arc minute resolution in this part of the galaxy as well. And so we can actually improve on sigma with the GBT. There are two open questions that I want to talk about here in my brief time. The first one is that we're trying to determine the properties and distribution of diffuse ionized gas in the disk. And for that, we're going to be using a recently completed survey called GDIGS, or the GBT Diffuse Ionized Gas Survey. And the second question is, what is the connection between diffuse ionized gas and ongoing star formation? So to answer this question, what I'm going to show you are some recent results from deep pointed observations around massive star formation regions. And these deeper observations are much more sensitive than what we have obtained in our large-scale maps. And so these two methods are very complementary, but they do service different science goals. Everything that I'm going to tell you about is going to be using radio recombination lines. And these are the radio analogs of the much more familiar optical line from the Balmer series, for example, H-alpha being our most prominent. And so we can use radio recombination lines to do a lot of the same physics that people have been doing for years in, say, H-alpha. The advantage, of course, is that we can detect the emission for radio recombination lines across the entire galactic disk, whereas H-alpha is limited by extinction. All right, so to answer our first question, like I said, we have recently completed this very large survey that we call GDIGS, and we hope to submit the paper in the very near future and then release all of the data to the community. The observational setup utilizes some relatively recent hardware improvements on the GBT that turned it into a recombination line machine for us. So what we use is called Vegas Mode 21, which gives us 64 simultaneous spectral windows, each with 23 megahertz. With these 64 windows, we can observe 22 alpha recombination lines. These are jumps in principal quantum number of 1. 26 betas, those are jumps of 2. 8 gammas, jumps of 3. And then a whole slew of molecular lines. This is all done at C-band, which also was recently upgraded and spans now 4 to 8 gigahertz. That upgrade was, I guess, not so recent anymore. Like Karen, I'm having trouble keeping track of time. So the utilization of C-band with its extremely wide bandwidth of 4 gigahertz simultaneously and Vegas with its 64 IFs is really, really powerful. We found that the baselines are not consistently good for a number of the lines, and that limits us to 15 good alpha lines. That's still quite a lot. So we have 15 lines that are consistently good, and then 7 of them show either persistent RFI or bad baseline structure, or sometimes we have problems crop up that when we're making our maps, it takes too long to sort out. But for the 15, they're always good. We can average all the data from those 15 lines to make fully sampled alpha maps at about 5.8 gigahertz and about 2 arc-minute resolution. The integration time per beam is 18 seconds per line, and so that doesn't sound like much, but actually that sensitivity is good enough to detect a significant amount of the ionized gas in the plane. All right, so rather than bore you with more specifics, here is some coverage. Up here we see the Spitzer composite, and Spitzer's nice because it shows you star formation clearly. Star formation is kind of the red areas or the bright green areas. GDIGS is this yellow box that extends from about 355 degrees longitude, so 5 degrees below the galactic center. And that's kind of the limit where we can map efficiently given the latitude and elevation coverage of the GBT. And then it goes all the way up to about 32 degrees. We have a couple little explorations, one at around 37 degrees and one around W49 at 43 degrees. And we have additionally started to map additional high mass star formation regions spread across the galaxy. I highlighted a couple here. Here's M17 and here's M16. And so we've collected data on those, and those will be published in a future paper. The noise is relatively consistent across the survey, and if you plot a histogram of all of the pixel values, we get a noise of about 23 millikelvin per 30 arcsecond pixel after averaging our 15 lines. So that's actually a very good noise, and it's very stable across the survey. So we were very happy with that. Of course, we can smooth spatially and spectrally also to get that noise level down. In the bottom 2 panels, we see the moment zero, so integrated intensity data from our survey. So taking all velocities and just averaging up the entire signal. The third panel down is simply the moment zero, whereas this one, all of the circles are discrete H2 regions. I tried to get a fancy PowerPoint animation in here, but I failed. What I can do though is do this zoom. Hopefully you guys can see that. So just zooming in here, we see the richness of these data. And you can see in the bottom panel that we have a lot of emission that extends out beyond the known H2 regions. And so this is truly diffuse ionized gas in the plane. And a lot of our follow-up projects are going to deal with the characteristics of that ionized gas and its connection to the discrete H2 regions. You can see that the galactic center here is particularly rich in ionized gas, as you might imagine. Another view of the same thing, I've just broken this up into velocity ranges. So this top one is 0 to 20, 20 to 40, 40 to 60, etc. And then the bottom panel is just a little movie of all of them with the velocity indicated at the top here. And so in a very general sense, you can see that the emission goes from right to left, so that in the lowest velocities, we have emission at the lowest longitudes. And then as you go up to the highest velocities down here, you have emission at the highest longitudes. That's just due to galactic rotation, but it's kind of pleasing to watch it. It's fun to see galactic rotation in action here. We see that we don't have much emission in the movie down here at negative velocities, so we're not sensitive to all the ionized gas that could exist in the galaxy, but we are very sensitive to gas that is in the scutum arm, and I'll show that on the next panel. We can zoom in here just to watch the movie a little bit more. Let's start here at lower longitudes. Oh, it doesn't play. Never mind. Sorry. All right, so here's our longitude velocity diagram. On the left here, this is the actual data. So what I've done to create these is I've simply collapsed down the latitude axis. So it's basically the analog of the moment zero that I showed 2 slides ago. In this case, though, we've collapsed latitude instead of velocity. The individual blue crosses here are simply the locations in longitude velocity of discrete H2 regions. So we can see a very good correlation between the GDIGS in color scale and the locations of the discrete H2 regions. That, of course, is not surprising. Most of the diffuse ionized gas in the plane can be explained as leaking out of discrete H2 regions, so we would expect an extremely good correlation between the locations of the H2 regions and the locations of the diffuse ionized gas detections. This here is, of course, the galactic center, where we have extremely intense emission and very, very broad lines. That's why it extends across the entire diagram. The right panel here is our Gaussian decomposition. So my grad student Dylan Linville has used something called GaussPy Plus, which is a Python package that automatically fits Gaussians to the data. So he's decomposed the data on the left panel into Gaussian components that we then reproduced on the right panel. And so it's just a cleaner version of the same exact data. But it more nicely highlights the agreement between the H2 regions here and the color scale GDIGS data in the background. All right, so that's my very, very brief overview of GDIGS. If you would like to know more, please ask questions or just ping me individually offline. I'm happy to talk more about GDIGS, but I didn't want to go into the weeds here. Instead, I wanted to highlight some recent work that we've been doing investigating diffuse ionized gas in the midplane. And so what we've been doing in more recent projects is looking at deep observations, so in this case 20 hours on one position, towards a previously undetected sightline where we don't really know anything about it, just to see if we can detect diffuse ionized gas throughout the entire galactic disk. GDIGS, like I said, is relatively shallow, although it's over 400 hours of total telescope time. The telescope time per integration is, of course, relatively low. So with the deep integration, we can get a signal that is not possible spread out over the entire map. So I'm showing you observations from one of our sight lines, but we're investigating many others. This one turns out to be the most interesting. This location in the center here is at 20 degrees galactic longitude and 0 degrees galactic latitude. Each of these circles is an H2 region of various classification, but the classifications don't matter so much. The red ones, though, tend to be brighter. And so we can see that this location is far enough away from the red circles that we wouldn't expect bright emission from discrete H2 regions to fall within the beam here. This one is 0.1 degrees away, so that's about 3 to 4 beams at our observing frequency. And this one is about 5 or 6 beams away. So we have 3 pointings, each in the galactic plane, with no previous detections of ionized gas emission in this direction. This is our data, and this view is kind of complicated, but I am quite proud of coming up with it, so you'll have to bear with me while I explain it. This again is a longitude-velocity diagram. The background in this case is CO. This is from the Galactic Ring Survey, the 13 CO Galactic Ring Survey by Jim Jackson et al. And so we see various components of the galaxy, but in CO, not in ionized gas in this case. The H2 regions are shown as either red circles if they have spectroscopic ionized gas detections, or in gray circles if they only have molecular velocities. Those are much less secure because it could just be a molecular cloud along the line of sight. These 3 spectra here are the 3 positions from this slide. The most sensitive one is here where we spent 20 hours, and these other 2 we only spent 1 hour each. The 20-hour position is in green, and we see that the noise is very low. We achieved 0.16 millikelvin RMS noise in this 20-hour integration. So it's one of the most sensitive spectra ever, actually. And we see 2 components in the green if you focus on that right now. There's a broad component that is at a similar velocity as a molecular gas, so no surprises there. But then we have this really weird narrow component here at about 110 kilometers per second. This velocity is not shared with any other H2 regions. You can kind of go north to south in this diagram. We see very little other H2 regions, very few other H2 regions in its vicinity. There's a couple other molecular line velocities, but again, we don't really believe those. The other 2 traces here in purple and blue are from this position and this position. And we see similar profiles. There's kind of a broad bit here. The purple one has an additional peak, but that's again fairly close to some of the other emission. But then they both have this component here at 110 kilometers per second with varying intensities. So as far as we know, this is truly diffuse gas. We have no idea where it comes from and cannot associate it with discrete H2 regions, which is different. In GDIGS, we can associate almost all of the emission with discrete H2 regions. In this case, we don't really know what's going on. So we're going to probe further positions in this vicinity to see if we can determine the spatial extent of this diffuse gas component. One hypothesis from Dana Balser is that maybe it's from the bar, which extends out to about 30 degrees longitude. The velocity field of the bar, though, is very difficult to model. So our first step is just figuring out the spatial extent of this signal. All right, so I've been kind of intimating here that the diffuse gas can be associated with discrete H2 regions. Part of that comes from work by my former student and now postdoc, Matteo Luisi, who
Lauren, I believe you dropped out for a moment there, right after you introduced Matteo.
Investigated how the recombination. Am I back yet?
Yes.
Okay, I told you that would happen. All right, so Matteo did this work on H2 regions spread out across the galaxy, and what he was looking for was how the recombination line intensity decreases from the center of the H2 region, extending out into the interstellar medium. So we know that photons can pass through the photodissociation region of H2 regions, and then they are in the interstellar medium, and they are free to ionize gas there, which has huge implications for the distribution of the ISM itself and for ongoing star formation. So I'm showing you here Orion, but this study looked at 8 other regions. And what we see is that if we look up into this plot, look at the red lines, or the red dots here, as you go outwards, so towards the right, we see the recombination line intensity decrease, as you might imagine. On this bottom one, we're looking at all of the regions, and I realize that this is pretty messy, but if you focus on a particular color, you can convince yourself that it can be fit with a line in this log linear space. And so these are power laws, and we can describe the radial fall off from the H2 region into the ISM as a power law. So the recombination line strength is decreasing as a power law, and is detectable out to a relatively large distance from the H2 region itself. We hope to continue this investigation with the GDIGS data, because now we have a very large sample of 1,000 H2 regions that are covered in the survey. All right, so that's my very, very brief overview of all of the stuff we're doing with the GVT. My overarching comment here is that the GVT is a fantastic instrument for recombination line studies, owing to its large instantaneous bandwidth at multiple wavelengths and its very, very powerful back end in Vegas. So GDIGS is right now complete. The recom line data will be available to the community very shortly. It gives a very complete view of the intergalaxy ionized gas and intergalaxy massive star formation. Deeper integrations, though, reveal strange spectral features that we have just begun to uncover. And then finally, the H2 regions themselves are going to leak a large number of ionizing photons into the ISM, and the decrease in recom line intensity is approximately a power law. All right, so that's all I've got now. I don't know if there's time for questions, but I'm certainly happy to answer them.
Hey, Lauren, we've got a few questions in the chat. You can either bring them up or I can read them out to you, whichever you would prefer to do.
I've got them here. Let's see. Yeah, so let's see. From Tom Bania, Loren, cite the effective T integration for the G20 position and show the G20 spectrum itself with an antenna temperature y-axis. Oh geez, the effective integration, I don't have that handy, but I can get the spectrum up if you give me a second. Let's see here. I don't have it handy. All right, we're gonna have to pause on that. I will find it though. Maybe if we have a second at the end, I can do that. Next question from Chris McKee. Does the 100 kilometer per second feature appear in all HN alpha lines? Just checking to make sure it is not an unidentified line. So I assume that this is from our diffuse gas investigation. And the answer is that it does appear in every single IF. So every single HN alpha spectral window does show this very narrow 110 kilometers per second feature in our very deep integration. That is something we checked. One of the interesting things is in this 20 hours, we were able to pull out some obscure molecular transitions, just one, I think, maybe one or two that we hadn't expected. Those do appear in single IFs, but this very bright feature, by bright I mean 8 millikelvin, is only appearing in, is appearing in every single IF. Mike Fitch says, is it a power law? The data looked exponential to me. Matteo actually did a statistical test of those two. They're very, very close. So a power law fits marginally better. So you're right, they certainly do look exponential, and you could convince yourself that they are exponential, but statistically a power law is a little bit better. Chris McKee says, what is the sensitivity of the deep integration in terms of emission measure? Ooh, let's see. Can I give that easily? Not super easily. I've got the equation here. If you guys don't mind a little bit of me digging around and stuff. Let's see. All right, so at our average frequency, the emission measure conversion in antenna temperature is that the emission measure is about 2 × 10⁵ times the antenna temperature. So this particular line is at about 8 millikelvin, and so that 2 × 10⁵ is in Kelvin. So that means that it's the emission measure, if I'm doing the conversion correctly, is about 10⁵. I think that's correct. Hold on. Matteo might be chatting. No, so I think about 10⁵ is the emission measure limit. The emission measure detection of that diffuse component. But as for the actual data, they're going to go down another order of magnitude, so about 10⁵ of that one. Let's see. So let's see, Tom Mania says the integration time is about 700 hours. Thank you, Tom. 700 hours, 20 hours per pointing, and then of course we average about 15 lines. And then he says that the ionized gas at all LSR velocities from the first quadrant line of sight positions. That is correct. We detect emission at everything between about 0 kilometers per second up to about 150 kilometers per second in that very, very deep integration. So we're fairly confident that we're getting everything along the line of sight. Thank you again, Tom. Do you see changes in properties? This is from Pedro. Do you see changes in properties, central velocity, peak intensity of the 100 kilometers per second recon line as a function of frequency in the deep integrations? That is a good question. And I know that factors into your modeling, and we have not investigated it. So we just finished these observations, I guess technically 2 nights ago. So we haven't explored too much about that sort of stuff, but that would be interesting to see if we can actually see changes with frequency. I don't know that yet.
All right, well, I think with that, we've finished all the questions. So I'd like to thank Loren again for this. I'd also like to use this as a quick way to advertise the fact that we're actually working on a new X-band feed, one that will be a bit cooler, have a wider bandwidth, and more stable baselines. And that X-band receiver should be hopefully out for commissioning, certainly next year sometime. So hopefully we'll get to see some even deeper observations once that's out. So with that, thank all of you guys for your time, and thank Loren and Jill for speaking. And hopefully we'll see many of you guys in 2 weeks. Bye-bye.